This is the AP1 static electricity information for electrostatics. You should have your notes packet, and a couple of things I want to remind you of. Make sure that you look up and know the definitions of all the vocabulary that's listed on the packet. Also, make sure you're visiting the video tutoring sites that are listed on your notes packet. They will be important as backup information. All right? Alright, so we're going to watch this because it has a lot to do about static electricity. When you go and fill up your tank with gas next time, make sure that you pay attention to the signs that are around the gas tank, okay? So, hopefully y'all will be able to hear this and it'll work.
So what are we doing at the Stoke Gas and Oil Laboratory in San Jose, California? Well, we're here to see whether we can accidentally blow up a gas station with a cell phone. No problem now with this static spark. It makes you right, and ignition comes easily. But what about this cell phone? Will it cruise into the cars and gas station fires? Nada. Yes. Say no. No phone. So Bob, have you heard of this method regarding exporting a gas station while using a cell phone? Not only do I hear it, I'm forwarding a minute that says, Mr. Rita says, don't use a cell phone that can cause fire in the pump. That email's gone around and people think that literally, but they are believing that when it's doing it. After researching hundreds of gas station fires, Bob Rita of the Control Group of the Institute says cell phones are the cleaner. Very simple. We don't have any accidents involving the cell phone and the service station. It's just us now. The dramatic fire shortened demonstration clearly shows what can happen when static is involved. People who re-enter the car during refueling face the biggest risk. But typically younger people, the older people will go like this to get out of the car. And when they do that, they risk first. They just simply pop out of the car. Not something not shut the door, not drown themselves, not like this, but they walk to the depth they're wearing heel-free shoes, so they're not discharging, they're not dissipating on the concrete. They have to keep the metal here. The vapors are coming out of the tank. The air is coming from outside. They have three parts of the fire triangle. The third part is sort of ignition to get the spark. The problem comes is when they overreact, they go, oh my goodness, and they reach the shaft to leave. They already have a fire, they get underneath the car, or they do it up themselves. They're busted. Absolutely. Isn't it definitely busted? No cell phone will ever cause gas station to ignite. Just not going to happen.
Alright, so they agree that it's not going to be a cell phone, but they did say that static charge could ignite gasoline vapors. So let's talk about static charge. Alright, electrostatics is really just the study of electric charges, forces, and fields. You might want to write that down as a definition. So if we need to pause, remember we can pause the video and you guys can write. Just let us know. Alright, there are two types of charges that exist. They are a positive and the negative. And they were actually named by Benjamin Franklin. He gets the credit. So what exactly is a positive and a negative? Believe it or not, you know a lot about this, and we're going to take a trip down memory lane to chemistry. Okay? We know that charged particles exist in an atom. We call them electrons for the negative and protons for the positive. Now, Benjamin Franklin didn't know anything about actually electrons and protons, but he did study a lot of behavior about static discharge and lightning. So he was able to look at the movement of charges without really knowing that they were electrons at the time. So our metric unit or SI unit of charge is going to now be known as the coulomb. All right, it's very much like meters, and kilograms, things like that. We'll just be talking about charge as a coulomb. Now, for every 1 coulomb we have, there's 6.25 times 10 to the 18th, either electrons or protons. Now, the charge is carried by the electron, and if it is carried by the electron, it's represented by a negative E or an E with a superscript of a negative sign. And if the charge carried is a proton, it's typically going to be given as a positive E. Now, the third particle, which carries no electrical charge, is that neutron, and we're not even going to worry about it because we're only worried about charged particles in electrostatics. So, when we talk about the charge of a single electron, it's actually going to be a negative 1.6 times 10 to the negative 19th coulombs. Now, for a proton, it's a positive 1.6 times 10 to the negative 19th coulombs. If you look at your formula chart, in your constants and conversions section of your formula chart, you have the electron charge magnitude. And that is where we're not really going to be worried about the sign so much. We know that electrons are negative, we know the protons are positive, but we're really more worried about that magnitude value, so we won't worry about the sign so much. But that number is given to you as 1.6 times 10 to the negative 19 coulombs on your formula chart, so you'll be able to use it, and you don't have to memorize it. Now, Ben knew that if you that certain things could, electrically neutral objects could be rubbed together and become charged. For example, when rubber is rubbed with a wool cloth, both of the objects are going to become charged. One is going to become a positive charge, and the other is going to become a negative. And what really happens is those electrons are ripped off of the fur or the wool, and then they're deposited onto that rubber. So that has an excess of electrons, so we make it negative. And the deficiency of electrons is going to be positive. You can actually do it with paper and a comb, and you can do it with your hair as well with a comb. So all those things happen. So really what we're doing is we're just scraping electrons from one and leaving them deposited on another. So we knew that a charge separation occurs also when you have a glass rod rubbed with silk cloth. So you got the silk to be actually negative and the glass rod would be positive. So in this case, the glass rod is going to lose negative charge and become positively charged, while the silk is going to gain negatives and become negatively charged. Now it's really important that you understand the only thing that ever gets to move is the electron. Write that down somewhere in your notes really good. Electrons, which are negative, is the only thing that can move. And that's because they're on the outside of the atom. Okay, the protons are stuck in the nucleus, so they can't move around. All right, so Ben experimented with the interaction of things, charged objects, and he suspended one and brought the other charged object near. And when he did that, if they were like charges, they actually repelled each other. And if they were unlike charges, they would actually attract each other. And again, if they were like charges, they would repel. You should write that down. Like charges repel each other, and unlike charges or opposites are going to attract. Let's watch this demonstration. I don't think there's any sound, so just watch. Didn't want to watch? So there's hanging tinsel, and a helium-filled conducting balloon, and a plexiglass rod, and a rubber rod, and some rabbit fur. Lots of fun electrons are available. So you took the plexiglass, hooked it. He did that so he could discharge any excess electrons that might be in the little tinsel. Whoopsie, there. He somehow got those to be charged, and now they're separated. And now they're attracted. And now he's going to discharge or take the excess electrons that are there out. get it to charge. And if they're like charges, they're going to repel, so they split apart. It's going to charge. Those are actually going to become oppositely charged because you can see how they interact with that tensile and they do opposite things to it. That means that the rubber rods are oppositely charged as well. So nice, he charged the rod. And he touched it, so he transferred electrons to it. And he touched it again, so he transferred more electrons to it. And he touched it again, so he transferred more electrons to it. And now finally, he has them like charged. And so they're going to repel each other. Pretty cool demonstration, even though there was no sound. Alright? So, he observed that like charges are going to repel, and unlike charges are going to attract. So there's also something called the principle of conservation of electric charge. Okay, conservation, things can't be created, we can't destroy them. Same thing is true for charge. All we can do is move it around from one substance to another, or even move it around within the same substance. So the negative charges are the only ones that can be transferred between two objects, so leaving one with an excess of positive charge and the other with an excess of negative charge. Now the quantity of excess charge on each object should be exactly the same, because the positive charge is coming from the fact that electrons were deposited on the other one. So if I took 3 electrons from one object and put them on another, then now I have an object that is a positive 3 charge and an object that has a negative 3 charge. Okay? So a positive charge is always going to be a shortage of electrons, and a negative charge is going to be an excess of electrons. So material can be electric in 3 different ways as well. So you need to know that you can have an insulator, which is going to hold electrons tightly, and they're not going to be free to move. Examples of this are going to be glass and rubber, plastic and wood, and that's why all of your wiring in your house is coated in plastic or rubber. And then you have conductor, and a conductor is a material where electrons are going to be free to move. Great examples are metal, such as copper, which is why all of the wiring in your house is copper. All right? Now, objects can actually become charged in 3 different ways, and you do need to know this as well. If you charge something by friction, it's just going to be rubbing electrons off of one and onto another. And that's always going to be done with insulators. Now, induction is when you're going to charge an object without touching it. You're just going to get near it with another charged object. Now, you can have induction with grounding, and you can have induction without grounding. So you do have 2 different types of induction that can take place, but you never touch it. And then you have conduction, which is where you charge something by actually making contact with another charged object. All right? So let's dive into these a little bit more detail. Friction, again, electrons are rubbed off of one insulator and onto another insulator. If you want, you can actually go to Colorado FET and do a simulation called balloons, and it actually will talk about rubbing or getting electrons off of one and putting it on off of a shirt and putting it onto a balloon and how that'll interact. But you can do that one on your own. I'll remind you this PowerPoint is also on my website, so you can double check it there. Now, charging by conduction, also, if it is touching an object, an uncharged object with a charged object, what you need to realize is when you charge by conduction, you're always going to end up with an object that is charged exactly the same way as the object that you touched it with. So this object is negative, and I'm going to touch this uncharged object. When I touch this uncharged object with a negatively charged rod, it's going to become negatively charged because I'm going to deposit some of these excess electrons onto the sphere. Okay? So charging by conduction will always result in an object with the same charge. Remember, if you ever need it paused, just say, please pause. Okay, to understand the last way of charging, though, we have to also talk about what happens to a neutral object when you bring a charged object near it. So when you bring a neutral object near a charged object, something called polarization is going to take place. And really, what polarization is it's going to be a separation of charges, so that you're going to have a slightly negative end and a slightly positive end. A lot like water. Water's a polar molecule because it has a slightly positive hydrogen side and a slightly negative oxygen end, where the two oxygens are. So polarization can occur in an actual object as well because of the movement of the electrons in the object. So if we bring a negatively charged object near this paper, all the atoms are going to line up so that the electrons can be furthest away from it. And if the electrons are all going to be furthest away, then the right side of the paper is going to be slightly negative, where the left side of the paper is going to be slightly positive. Now this will cause the next piece of paper to do the same thing, and the positive end of the next piece of paper is going to be attracted to the negative end of this paper, and so on and so forth. And that's why you could actually pick them up in strings. We'll do a lab where I'll actually allow you to do this in class, and you'll be able to see how it works. Okay, polarization occurs because electrons are attracted or repelled to the charged object. This process is temporary, and it is just the temporary separation of the charges. So an attraction will result. So the electrons are free to move in metals, so they would move around accordingly, and they would move away from the negative charge. All right? Now, if you're charging by induction with grounding, you're going to end up with a permanent charge. If you're doing it without grounding, you're going to get a temporary charge, and then it'll just go back to normal after you take the charged object away. But if you have polarization, when I bring this charged object near, I'm going to polarize this sphere, but then I'm going to attach a grounding wire to it. When I attach a grounding wire to it, that's going to allow for the movement of electrons, either out of the sphere or up from the ground into the sphere. Since I'm near it with a negatively charged rod, the electrons are going to be like, we're out of here. We want to get as far away from this rod as we can. So they're going to go down to through the grounding wire into the ground. And so when you take the grounding wire away and you take the actual charged rod away, then you're going to leave it with a positive charge. So something that you need to understand with induction, if you have grounding, you're going to have polarization, then you're going to have grounding, and then you're going to end up with an object that is oppositely charged from your charging object. Okay? So the resulting charge on the object is always going to be opposite of the charging object. So an electroscope is actually a device that's going to detect static charge. That's definitional. You need to know that. Okay? It is made up of a knob with a rod that's all metal and has leaves that are attached to it that are also metal. And so if I bring a negatively charged rod near it, then the negatives that are all in this metal are going to go down into the leaves. Since the leaves are going to have all the negative charge, they're going to want to separate from each other. So you'll be able to see that. If you touch it with a positively charged rod, then you're going to make it positively charged and they'll separate as well. So we'll talk about the electroscope, but you really can't tell whether you're getting near it with a positive or a negative. You'll just know that if it's charged, the leaves are going to separate apart. Okay? And we'll talk about how if you touch it, that makes a difference, whether if you just get near it, you'll be able to see that separation of leaves. Now, grounding is another vocabulary word, and it's really just allowing charges to move freely along a connection between a conductor and the ground. The earth is a great ground. That's why we pick up electrons when we walk around, and then we deposit them somewhere else. And that's why we shock each other when it's cold outside and things like that. So here, a positively charged rod is brought near, so electrons want to come up into the electroscope, whereas here, a negatively charged rod is brought near, so the electrons want to move out of the sphere into the ground. So electrons can move either way. They can move into or out of, depending on whether they're attracted or repelled. So to review, This is induction with grounding. So we start with polarization. Then we're going to raise our hand up into it, and we're going to allow the charge to escape by grounding it. And then we're going to take the charged object away, which is going to leave the sphere with an opposite charge. Okay? So after this recording, you should be able to spend the rest of the time actually doing your static worksheet, which is inside your packet. So you should be able to spend some time doing that. If you run out of time this class, you can spend about 10 minutes next class doing it as well. So remember, induction with grounding, and I will put that preface in there, induction with grounding will result in an opposite charge, and conduction will result in the same charge. Now, why is electrostatic charging even important in our real world? First of all, you can take a fine mist of negatively charged gold particles. When they spray them out, they'll become negatively charged, and they'll actually adhere to positively charged protein that's left on a fingerprint of money. The reason they use gold dust to fingerprint money is because it'll come off easier in the long run, and it's not such a big deal. Whereas if you used regular fingerprinting powder, that would be a problem because it would actually destroy the money, and you're not allowed to do that. So when they use money and they're trying to get fingerprints from it, they actually use the gold particles. Also, your cars are painted by using electrostatic charging because the paint becomes negatively charged, and it'll adhere to the positively charged metal because the metal's been buffed so much that the electrons come off of the buffer with the buffer, and it leaves the metal positively charged. So when the actual paint is sprayed onto it, it's attracted to it, so it sticks better, and then they bake it and do some other things to keep it stronger too. But that's why paint's really actually hard to get off of your car. Okay? With that, we are going to stop this video, and we will move on later to the rest. All right, you guys can do your statics worksheet.